There are three types of orbitals that we'll encounter most often, and they are S, P, and D. So the S orbitals are spherical, the P orbitals are dumbbell shaped, and the D orbitals can have a couple of different shapes. We'll start by looking at the S orbitals in a little bit of depth. So S orbitals are spherically symmetric, and they're centered on the nucleus of the atom. So in this diagram, the intersection of the X, Y, and Z axes is the nucleus of that atom. And remember that these things behave like standing waves, and so they have different harmonics and different nodes. So if we look at our lowest energy S orbital, the 1s orbital, where the number out in front is simply the principal quantum number. If we look at our 1s orbital, we can see how the probability of finding that electron changes as you move further away and closer to the nucleus. So close to the nucleus, there's a very, very low probability of finding an electron, right? If you're exactly at the nucleus, you can't have an electron be superimposed on the proton. So there's very low likelihood of finding an electron there. And as you move further away from the nucleus, the probability of finding an electron goes up. And eventually you can get very, very, very far from the nucleus, and the probability of finding that electron goes down. Right? If you have a nucleus of an atom that is centered in your bedroom, for example, you're not going to find the electron on the other side of the world. Right? The probability goes down as distance increases. And if you look at the 2s orbital, right, so the second higher energy s orbital, what you'll find is that there's now a node. So now you have, again, at the nucleus, zero likelihood of finding an electron. And a little bit further away from the nucleus, you have some probability of finding an electron. Not very much. Then you have a node where there's zero likelihood of finding that electron. And then further away, you end up with a much higher likelihood of finding that electron. And then in our 3s example, so our third s orbital, so higher energy again, you have two nodes. What you might be able to see is that as the principal quantum number gets bigger, the majority of the probability is going to be located further and further away from the nucleus. And what that translates to in kind of three-dimensional terms is the bigger your principal quantum number, the bigger your orbital is. So the 1s orbital is quite small, and the 2s orbital is bigger, and the 3s is bigger again. And now we'll look at the p orbitals. In many ways, the p orbitals are very much like the s orbitals. They represent probabilities. As you get to higher and higher values of n, they get larger, and they also have nodes within their lobes. They're a bit different, though, in that their symmetry is not spherical. They can take different orientations in space. So the p orbitals come in sets of 3, and we describe them as aligning along the Cartesian axes. So we have one of the 3 orbitals aligns along the x-axis, and we typically represent it as a horizontally drawn dumbbell. The pz orbital is one we represent as being along the z-axis, and we represent that as an up and down orbital. And the py orbital is one we represent along the y-axis, going into and out of the board. Typically we represent that by drawing something at an angle. Now, it's important to note that all 3 of these different orientations have exactly the same energy. Any set of 3 p orbitals are going to be indistinguishable from one another. So labeling these px, py, and pz is just sort of an arbitrary thing. And the third type of orbital that we'll talk about that we'll encounter regularly are the d orbitals. And the d orbitals come in sets of 5. So there are 5 different types of orbitals. 4 of them are exactly the same shape, but in different orientations. All 4 of these orbitals are identical in shape. They're just oriented along different planes. And the 5th orbital is exactly equal in energy to the other 4, but it has a different shape. And similar to the s and p orbitals, they get bigger with increasing value of n, the increasing principal quantum number, and they have notes. The difference is largely in their shapes.